Alex Kozen. I'm an assistant professor in the physics department at the University of Vermont, but I've spent most of my career at University of Maryland, about the past 15 years, working on ALD for battery materials for the most part. So I'm going to be talking about how ALD can be used in advanced batteries, particularly solid-state batteries, sort of the next generation of technology that's coming up. Will this work? There we go. I'll start by advertising Vermont a little bit. So this is the view from the physics building at University of Vermont over Lake Champlain and over the city of Burlington. So for any of you who aren't from the US, Vermont is up here, and Burlington is in the northwest corner of Vermont. We're awfully close to Canada. We're about an hour and a half from Montreal. That's the closest, biggest city. Burlington itself is 44,000 people, so it's not a very big city. But you know, Vermont itself is best known for maple syrup, Ben & Jerry's ice cream, and our #1 export, Bernie Sanders, who's the most famous person in the state. So I moved there in December. I've already seen him downtown twice, hanging out, which is pretty cool. So it's small enough you get to see people like that around. And yeah, the University of Vermont is founded in 1791. The Marquis de Lafayette actually laid the cornerstone of the mill building right here. So he laid that cornerstone in 1791, which is pretty cool. There's a long history. So it's one of the oldest public universities in the United States with about 12,300 students or so as of this year. So the history of solid-state batteries is really the history of solid electrolyte materials, because these are the key enabling technology to make solid-state batteries possible. And so the first solid electrolyte was discovered by Michael Faraday in the early 1830s. He looked at silver conduction and lead ion conduction in lead fluoride and silver sulfide materials, and basically started the solid-state ionics field. That didn't go very far for a long time until the late 60s, when Ford developed the first batteries with a solid electrolyte using lithium beta alumina sintered membranes, but then they had to operate at very high temperature because of the low conductivity of these solid electrolyte materials. And so these had to operate in the hundreds of C using molten sodium and molten sulfur as the anode and the cathode in this case. And then the first thin film battery was developed at Oak Ridge National Lab by Dudney and Bates in the early 90s. And this was the first thin film solid electrolyte technology. So that was when LiPon was developed in the US. And then in 2007, Peter Naughton came around and said, we could take processes that are used in the semiconductor industry. We could take substrates that are used in the semiconductor industry. In fact, this is pretty much a DRAM right here. My laser's not working. This is pretty much a DRAM structure in silicon, and we can just deposit all the active layers of a battery in there one by one using vapor deposition processes. But he was ahead of his time, because these processes for these materials did not exist yet. And so, he was visionary in that this should be possible, but it took until 2018 where my group at University of Maryland developed the first solid-state battery, 3D solid-state battery using ALD for every layer of the process. And so that was quite arduous, but this was done in reactive ion etched silicon trenches with every active layer, all the way from ruthenium bottom current collector, ruthenium bottom contact, lithium vanadium oxide cathode, lithium phosphorus oxynitride solid electrolyte, tin oxynitride anode, and then a tin nitride anode current collector, all with ALD in the same chamber. So let's take a step back and talk about where are we today with conventional batteries. And conventional batteries are basically made out of dirt, and you're competing with dirt. And dirt actually works pretty well. It's been very highly optimized over the past 40 years or so of technology development. But this is a cross-section here of a Chevy Volt battery. And so this is a prismatic cell. You can see the different layers of, you have the anode current collector in copper here, a cathode current collector in aluminum. You have anode materials and cathode materials in thick films, hundreds of microns sandwiched in between those layers, and then in a like aluminum foil package. But you can see each one of these layers, you have a bunch of particles in the anode side, or cathode side, a bunch of particles in the anode side with a polymeric separator in between, and those are all bathed in a liquid electrolyte to enable good ion conduction and good contact to all these particles. Of course, the problem is these particles, some of them are relatively large in the tens of microns in diameter, and so ion transport through these particles is typically very, very slow. And if you have a range of particle sizes, when you charge and discharge your battery at a certain rate, you either have a bunch of particles that can become overcharged, if you charge too fast and say some particles are too small, or you don't utilize all your active material if some of these particles are too big and you can't get lithium into the middle in the time that it takes to charge your battery. And so this inhomogeneity is very problematic, and you lose a lot of optimization of the cells. And so, there are basically two ways to package these modern batteries. One is a prismatic cell here. The other is a jelly roll, where you basically roll this up and put it in a little stainless steel can. That's what Tesla has typically used. And the 18650 was the commercial standard for a number of years. That's been superseded by larger sizes now to reduce the amount of packaging and increase the amount of active material inside the battery. But really the problem is that these are still bathed in liquid electrolyte, and when they overheat, if you charge too fast, if you have a catastrophic damage, that can be catastrophic and very energetic. So really, if you want to improve battery performance, improve the safety, there are really two ways to do this in batteries. So one way is to improve the battery materials. This is the route that A123 took, a startup company out of based in Massachusetts, and they folded years ago now. But their whole idea was, we can take lithium iron phosphate and replace the lithium cobalt oxide in the cathode, one-to-one replacement. Great idea. It's now commercialized again, and it's in production in vehicles. But they were ahead of their time, and economics didn't work out. It was too early for that type of work. But there are a lot of opportunities for new materials and batteries. And the problem is, cost is an issue, commercial viability is an issue for some of these materials, given the massive scale that you need for the battery industry. The other approach to improve the performance of these cells is nanoengineering. And basically, again, if you have these thick films or thick layers, large particles in the tens of microns of size, it can take a long time to get electrons and ions to make contact inside these particles. And so that can really slow down your charge and discharge rates. So if you shrink the active material to something like a nanowire, you can get very, very good ion transport through those materials if it's small. But then something like a nanowire, given the low conductivity of most electrode materials, it can take a long time for an electron to percolate all the way up to the top of those nanowires. And so really the ideal structure is a nanowire or some kind of nanoheterostructure where you have intimate contact, very thin layers with your electrode and your active material. So you have very small distances for electron and ions to move before they can recombine in these materials. So where are the opportunities here for ALD to improve batteries? And there are actually quite a few. So again, active ion materials for ion transport. You can make new materials as thin film materials. So lithium cobalt oxide, lithium manganese oxide, lithium iron phosphate. Those have all been developed in terms of ALD processes. Those are the three most used commercial particles. And so that enables you to do a one-to-one particle to thin film architecture transition using the same materials that are already known. But you can also work on new materials, for example, V2O5, ruthenium oxide, niobium bronzes, some of these more interesting materials that have emerging properties that are pretty exciting. And this really started taking off right when I started my PhD in 2009. So there were 4 papers on ALD for batteries, and then right when we started, it started taking off. And so it's gotten more and more popular over the years. Again, going from materials that are used as active materials for ion storage to surface coatings and passivation. So some of the work that like Forge Nano and Steve George, his early work, Andrew Kavanaugh of coating existing particle-based electrodes has been quite effective. And in fact, major companies now, Tesla uses lithium niobium oxide as a cathode coating in their commercially produced cells. And there are other chemistries that are also used commercially by other vendors in terms of electrode passivation. And interestingly enough, you can buy lithium niobate coated particles on Amazon.com for making batteries. So it's actually pretty easy to get them. But then the last contribution is, again, being able to make these integrated architectures and not only coat particles to improve their performance, but create these fully integrated 3D devices using only thin films to make batteries where you have much higher utilization of active materials and much more control over architecture and geometry. So, let's start with those materials and nanostructuring. What does that really get you? Okay, so electrostatic capacitors, we'll start up on the top left here. Think of it like a lean muscle formula, right? You get a lot of energy very, very fast. So you can pump that iron, but then you're not going to hibernate through the winter. You're not going to hold on to that, right? It disappears very, very quickly. So that's very high power delivery. On the other side of things, you have a conventional battery, which is kind of like a giant block of lard. you can hold that energy and store it for a very long time, but you can't eat that lard very fast. And if you eat all of it, you're not going to move very fast afterwards. So it's a very, high energy density, but very, very slow delivery of that energy. And of course, electrolytic capacitors are somewhere in the middle. And so if you start making these nano-heterostructures with thin active layer materials, integrated current collectors, you can dramatically improve the performance of all of these devices in terms of making MIM capacitors up here in the top left, electrostatic capacitors, and then really, our demonstration of this concept is the nanopore battery, what we call it. So this was a battery we built using all ALD layers in an anodic aluminum oxide template. So it's anodized aluminum. You take a sheet of aluminum foil, anodize it to create nanopores, and then we actually we tuned the ALD process to reduce the conformality so we could control how far the materials infiltrated from each side of that aluminum oxide. And then you can actually grow an anode and a current collector on one side, cathode and current collector on the other side. In this case, it was a proof of concept demonstration, so we used vanadium oxide for each side, so it's really a symmetric battery. The advantage here is that you can get a 24-second discharge or charge of this cell at 50% theoretical capacity for the materials. So that's pretty crazy. You can imagine driving into a gas station, electric station, whatever you call it, plugging in your car, 24 seconds, you're 50% charged. That's pretty amazing. So that really shows you dramatically how important these very, very thin structures, nanostructuring is to this high power performance. And then, of course, at a 1C rate, which is a 1-hour charge discharge, we are actually at theoretical capacity for the materials. So, good as vanadium oxide can be, you are using 100% of that material, and it's very, very efficient. The problem with this is it was still using a liquid electrolyte. We had to bathe the electrolyte inside the pores to make it work because we hadn't developed a solid electrolyte process yet to facilitate this. So, the work at Maryland that we have done over the years, we developed the APON family of solid electrolytes, or the alkali PONs. These are polyphosphazine. They're alkali phosphonitride glasses. We have two processes for plasma. So the lithium and the sodium counterpart, that's a lower temperature process, but it's slightly more directional, but it has a lot more tunability in that you can control the conductivity by titrating the nitrogen plasma incorporation into the material. And then we also have some higher temperature processes for a lithium, sodium, and potassium analog of the APONs. The potassium one does not work very well. Conductivity is incredibly poor, but it's much faster because it's a 2-component instead of a 4-component process. Limited tunability, but that nitrogen to nitrogen to phosphorus ratio is fixed because it's fixed in the backbone of the precursor, and so that's built into your system. So you get very good conductivity in that phosphate backbone, better conductivity. But the limitation of this is that it's a much higher temperature process, and it really only works about 350 C and above, so it limits the types of devices and structures you can make. And of course, you might have asked, well, does conformality matter with some of these nanostructures, right? Yes, it does. So here's an example of this is a 2.5D battery. So this is what we had and we were working on before we had fully developed the ALD processes to make the 3D battery. So we have here a current collector in platinum sputtered on actually a FinFET substrate. And then lithium cobalt oxide sputtered on top of that. And then silicon's the anode and copper on top. So that silicon and copper are planar on top because we couldn't get those into the pores. And so you'll see there are huge voids in this in here. So we have very low utilization overall, the scaffold. The lithium cobalt oxide is much thinner at the bottom, much thicker at the top. So you get very poor utilization of the actual material, and you get shorting at these bottom corners. And you can see there's massive inhomogeneities in the cycling. So that's really a non-optimized structure, and it really says if you want to make these 3D devices with thin films, you have to go to atomic layer deposition for the materials. And so again, you go to ALD, and it works great. And so this is the same battery that I showed you before, a little higher resolution view, reactive ion etched silicon substrate. Again, we deposit every layer sequentially into the batteries, so ruthenium, lithium vanadium oxide, lithium phosphorus oxynitride, tin oxynitride, and then titanium nitride is the top contact. And the layers are so thin, we're not even filling up this pore. The layers are here conformal on the top, and on the bottom, it's a little hard to see in this SEM images, but all the layers are here stacked. And each one of these is between 10 and 50 nanometers thick. Of course, if you want to improve the power density of this, you want to go to a higher aspect ratio, thinner layers, higher aspect ratio, higher surface area. So a higher surface area gives you higher lithium flux, gives you higher power density, higher aspect ratio, just gives you more material in general, so increases that cathode loading that's available in your device. And so some of the simulations that we have here, basically this cell that we published with an aspect ratio of 2 for the initial proof of concept with a dry etch silicon is right about here. So this is a, AEF 10. So that's an area enhancement factor of 10 over a planar battery in terms of improving the surface area. And you can see this is basically, slightly better than some planar cells, but not really that dramatic in terms of power performance and energy density. But of course, if you simulate a cell moving to something like in an anodic aluminum oxide template, again, which much smaller, higher pore density, smaller pores, but higher pore density, much less scaffold, you get much better utilization, and we can move to a dramatically improved power and both power density, energy density, and these are actually better than 18650 cells in terms of both. So some of the uses of these ALD materials for advanced batteries other than these 3D solid state batteries, right? And one useful approach is stabilizing the anode metal surface in basically lithium metal anode batteries. And so we've done some of this work at Maryland, and Neil Dasgupta and his group at Michigan have done some excellent work also coating lithium metal. And basically with a 15 nanometer aluminum oxide coating on just a piece of aluminum metal, you can get a pretty, these are backwards. This is the uncoated, this is the coated lithium. The coated one corrodes and turns black after about a day in the air, where about a 15 nanometer aluminum oxide coating directly on the lithium does not corrode after a day in the air. It actually does a little bit. There's a little spot right here where I touched it with tweezers, and you can see that, so I'm not faking it. It does actually turn black where you break the ALD coating. And that ends up dramatically improving the performance when you cycle these batteries. In terms of a lithium sulfur cell, you can get about a 50% increase in capacity over 100 cycles just by passivating the anode, preventing the parasitic polysulfide shuttle reaction. And you can see the dramatic difference here when you take these two cells apart. The ALD passivated anode is much, much cleaner than the unpassivated anode, which has quite a bit of lithium polysulfides deposited on the surface. And if you go in and you look at, this is a different system. This was done with a carbonate-based conventional electrolyte and not a lithium sulfur cell, but this is Neil Dasgupta's work. And you can see there's a clear difference in the ALD-coated lithium and the uncoated lithium in terms of morphology and in terms of cycling performance and behavior of the cell. And this is after 715 cycles. So this, the coating is there after a very, very long time of plating and stripping lithium. And then in terms of dendrite performance and preventing dendrites, if you look at the top right here, you can see that's uncycled. You have lots of dendrites, lots of mossy lithium, lots of uncontrolled morphology of your surface, which leads to a lot of reduction in capacity over time. And then this paper, we actually started with a polymeric layer on the lithium and then put an ALD layer on top of that. That has to do with the interaction of certain ALD processes with lithium metal, and there's some issues with nucleation and growth. And so this was a way to short circuit that and enable lipon deposition directly on lithium metal without too many defects. And so you can see that really stabilizes the surface when we're cycling at, this is 2 milliamps per centimeter squared, which is far above the dendrite production threshold for lithium ion batteries. So you can be cycling at a very, very high rate, all things considered, and get a very stable surface of the lithium with much cleaner stripping and plating of that lithium. So another major use of ALD layers and ALD solid electrolytes in lithium-ion batteries is electrochemical stability at these solid-state interfaces. So if you look at the potential stability of the sulfides over here and the oxide solid electrolytes, basically most of them are not stable at lithium metal potentials or at very high voltage cathode potentials. So basically down to 1 volt or up to about 4.5 or 5 volts. And so what that says is if you put this material in contact with something that has an electrochemical potential lower than about 1.5 volts, it will start to decompose into its constituent components. Depending on the material, that can be very poorly controlled. And so you end up with these complex materials that decompose into their binaries. Some of them have higher conductivity than others, and it's just hard to control this process, and you end up getting higher impedance layers at those interfaces. And so if you can take an ALD process and create a solid electrolyte interface, either on the anode side or on the cathode side, you can bridge the intrinsic electrochemical window from the electrolyte itself and extend it all the way to lower anode potentials and higher cathode potentials. which then lets you get much higher power density of your battery without decomposing the electrolyte, and ends up giving you much lower impedance of these cells. And also, there's something to be said here. Even some of the solid electrolytes, for example, lithium phosphorus oxynitride, that's a 4-component material. That is thought to be stable at lithium metal interfaces, but it's stable because it decomposes into its binary components, most of which are pretty highly conductive. So Li3P, Li3N are awfully ionically conductive, and so it's a very stable conductive interface. And so LiPoN is considered the only solid electrolyte stable at lithium metal potentials. It turns out if you put a sub-nanometer aluminum oxide ALD layer before the LiPoN, you can prevent this decomposition of the LiPoN and actually improve the performance even more. So there's an advantage of heterostructured layers and be able to make very, very thin tunable layers at these interfaces to improve the performance. So something else that's another use of ALD layers in advanced batteries is for example, lithium cobalt oxide with no cathode coating. As you cycle it back and forth, the material, it undergoes a relatively low, about 2.5–3% volume expansion with lithium cobalt oxide. There's a phase change associated with that. But this can result in fatigue over time, breaking of the materials, they can decompose, and you also get some cobalt dissolution into your electrolyte and cobalt diffusion out of your LCO materials. And so coating the cathode with some solid electrolyte, in this case lithium cobalt zirconium oxide, but you can choose a number of materials, can prevent that cobalt dissolution and prevent dissolution of materials in your cathode from going into your electrolyte. Also stabilize some of these phase changes and mitigate some of that pulverization of the electrode. And that's really evident in some of the newer anode materials, conversion electrode materials. So instead of an intercalation material, these rely on a chemical conversion reaction where you form lithium oxide plus a metal. And then you repeat that process back and forth. So you pull the lithium out and you have a metal oxide and then lithium. And that conversion is your electrochemical lithiation. When you do that without any coating, not only do you pulverize the material and form a bunch of nanoparticles, which then are poorly connected and end up falling apart, but you form a rather large SEI, organic SEI on the surface of these materials. And of course, if you put a thin solid electrolyte coating on the surface of these materials, so this is a ruthenium oxide ALD particle on a carbon nanotube, we put LiPoN on top of that. That can chemically clamp the material, prevent it from pulverizing and falling apart, and you end up with much, much higher capacity retention. Again, it's about a 50% capacity retention with a very, very thin ALD layer at the same power performance. So you're not sacrificing power performance either, which is really critical. And you're not dramatically increasing the impedance of the entire cell. Another critical aspect of this, and going back to solid-state batteries here, so next generation, and I know I'm bouncing all over the place, but I wanted to keep this short and I didn't want to include too much, so please bear with me. But improving the contact. So a lot of these solid electrolyte materials, for instance, LLDO, LATP, form a carbonate layer on the surface, and that carbonate layer can basically you don't get very good wettability of the lithium on the surface. And so you can do two things to improve the wettability of lithium on the surface of that electrolyte. You can either etch off your carbonate layer, or you can deposit another ALD layer that will improve wettability, will alloy with the lithium, and enable you to have much better wettability, better contact with the surface. And this is really critical cycling. You basically get much better interface contact, and you don't get these voids forming upon repeated cycling, so you end up with much better capacity over time. So another big challenge is the conductivity of these solid electrolyte materials. And so, most ALD solid electrolytes that have been developed, and there have been about 15 so far that have been published, most of them are down here, 10 to the minus 7 to 10 to the minus 9 Siemens per centimeter, unfortunately, which is a little too low to enable good power performance for batteries. The highest conductivity solid electrolyte published with ALD is from the Dasgupta group at Michigan, LBCO, I believe. But that's still 2 times 10 to the minus 6 Siemens per centimeter. So it's not as good as commercial liquid equivalents, which are up here, 10 to the minus 2 Siemens per centimeter. So there's a large gap in terms of improving to meet the same performance as liquid electrolyte-based batteries that exist today. But there are a lot of solid electrolyte materials that have been developed in powder form. So these materials exist, they've been characterized. Many of them have conductivities far higher than what we can develop with ALD. And so one of the challenges with ALD here is that composition, a lot of these materials are quaternary, pentary materials. They're very complex to make with ALD. So these processes are very, very difficult. A lot of the time you also, if you have the composition correct, you don't necessarily end up with the right phase either. So you need composition and you need crystal structure at the same time. And that can be very, very difficult with these complex materials. You can get things like spinodal decomposition, phase segregation. So keeping homogeneous materials is really, really critical. And there's a lot of opportunity for improvement here. Gerd Cedar has done some recent work that shows basically moving to high entropy materials in terms of these solid electrolytes. So you get anionic substitution in the lattice. So you go, you start substituting 7 or 8 materials into, say, LaZO or something. You can, dramatically improve the conductivity by a couple orders of magnitude. And so I think that's a good opportunity to start working on these complex materials and start improving the conductivity, pushing the limits of what's possible. And I will say we have one of these materials working. I won't tell you which, but it's pretty exciting. One of the big challenges with these solid-state batteries and solid-state battery materials and solid-state electrolytes is they're inherently unstable, and they have mobile lithium in them. And so, of course, if you hit them with some kind of electron beam, or you hit them with a plasma and you put a bias on these materials, you're going to move the lithium around, and it may not go where you want it to go. In fact, usually it doesn't, and usually it causes all sorts of problems. And this has really been a huge challenge developing these types of devices, developing these materials. So for example, this is a solid-state battery we made and exposed to air for about 10 minutes, and it destroyed itself very quickly. That was not viable. Here's an example of a LiPON, lithium phosphorus oxynitride, ALD, on a carbon nanotube. We were just trying to image it in a TEM, and you can see after 180 seconds, we have melted the solid electrolyte with an electron beam. So they're very, very sensitive to damage. So characterization of these can be pretty difficult. So for example, this is a fib we did in-house of a sodium-ion solid-state battery using a sodium phosphorus oxynitride electrolyte. This is a planar version just for characterization. But when you fib through, basically you end up with mush, and who knows what was there in the first place. It's hard to tell if there was damage during processing, damage during deposition, or if this was an artifact of the actual characterization process. And so we had to partner with SINT in Sandia Labs to do fib milling and STEM imaging, cryo milling and imaging. And the advantage is you cool everything down to 140°C, do the sample prep, do the analysis, and it turns out you get a much better image of the materials, but you can still see, so here's a gold top contact, here's a sodium oxynitride, vanadium oxide cathode here. You have a large mixing layer that's induced between the two. So there's some interaction with the lithium-containing materials deposited on some other material that doesn't contain lithium. You have a large interphase that's formed between the two that is maybe difficult to control. So this is something that's a continual challenge for these materials, and just understanding how they behave and characterizing them can be difficult. Now, a big opportunity for being able to use thin film solid-state electrochemical materials is to use solid-state batteries as scientific discovery platforms, for example. So on the left here, what you can see is this is sort of a deconstructed solid-state battery array. So what you do is you can make a solid-state battery, and everything in the middle is a solid-state battery: current collector, anode, electrolyte, cathode. Current collector. I think I missed one. Anyway, everything in the middle is a solid-state battery. So you have an array of devices to test device functionality, and then to test a whole bunch of these different parameters in the devices and look at device statistics. But what you also have are you have diagnostic devices on the same wafer on the side. And so they let you deconstruct the battery. You can look at anode electrolyte interactions. You can look at cathode electrolyte interactions, and you can figure out where are the problems with these devices, with these depositions. Is it in the processing? Is it in the characterization? Because you have the entire battery deconstructed and pulled apart in terms of different subcomponents on wafer. And so this is really, really powerful. And then, of course, if you follow the same thing through and you make something that is made like a battery, but maybe doesn't look like a battery. So for example, this is a thin film system, which is, current collector, cathode, electrolyte, anode, but it's designed to be a discovery platform. So for example, you can run this, you can cycle it as a battery, and then you can analyze the materials with some in situ technique using a device that you have patterned and made with pristine materials to understand how these materials behave and how these materials degrade, which is really, really powerful. You can then take this knowledge and feed that back into conventional battery manufacturing, and you can say, now we have a better understanding of how the state of charge improves, say, electrical properties, optical properties of these materials, and it really gives you much more capability in terms of analysis and characterization. One big challenge for us in making these devices is patterning. Patterning of lithium-containing materials is very, very hard, especially some of these ALD lithium-containing materials. And so we have struggled with patterning a lot of these devices. And so there's a big opportunity for better ways to pattern thin film devices, thin film platforms, where you don't have, say, a penumbra effect from a shadow mask, which really limits your feature size. I will say feature sizes are typically limited by what a student can do and what they can hit with a probe in a glove box, which is bigger than you would like. But patterning itself is a challenge, even at the millimeter scale with some of these devices and materials, because you really do need excellent uniformity so you get good homogeneous utilization of the electrodes and the materials. And if you have something like a thickness fall off even over a couple 100 microns on the edge, then that can give you, very, very poor performance, and you're not necessarily understanding the device at the level you would like to. So just to sort of take a look at manufacturability and how you would make these devices, right? So here's an 18650. This is a Panasonic 18650 right up here. So if you assume that that has some X power density and some X energy density, if you can make a thin film solid state battery, so let's assume some arbitrary conditions of solid state battery, and the assumptions we made with our simulations here are that it has a 300 nanometer thick V2O5 cathode. We use V2O5 cathodes all the time because the ALD process is great. We understand the material well, it behaves well, we can work with it. It's a good prototype, but it's never going to be in production as a production battery. But it's a good prototype to understand how they work. So same power density, same energy density. I'm sorry, half the size of an 18650 for 10 times the power density at the same energy density. So this solid state battery cell, this is a 50 layer cell. That has the 10 times the power performance of an 18650 at half the size. And if we call this the low power thin film solid state battery. That one has the same power density as an 18650, but it's about a quarter of the size of an 18650. So there's about a 4-fold increase in volumetric energy density, even with non-optimized materials of some of these thin film batteries. So there is a huge improvement in device geometry and architecture. And then, of course, a single thin film solid state battery is quite a bit smaller and is on the order of hundreds of nanometers high and can be integrated with silicon manufacturing. So really, there are two ways to scale this up. One is to take I would call it the low energy of entry approach, low barrier for entry approach. You basically take a battery as it's been made today, but you replace that liquid electrolyte with a solid electrolyte somehow. And maybe the first step is just coating the particles that go into a cathode in a conventional battery. And so this is something that Forge Nano has done quite a bit. Here's an example of one of their tools. This deposition tool for coating particles, this is like 2 stories tall. I can't remember if it's called the Prometheus or the Hercules, but it's massive. And it can coat kilotons of particle material with ALD coatings. That does improve the performance of some of these materials, but it's not going to get us to a, technology that leaps beyond what we have now, right? So the way that I think is the way forward is to move into more specialty applications, to use the established semiconductor manufacturing industry, the techniques, the tools, the processes, but you put in other materials and you make batteries instead. You don't need small feature sizes, so you can get away with a trailing edge fab. You don't need a leading edge fab, right? You can get away with something that's 40 years old that can't make money printing semiconductors anymore. You just put new materials in and start printing batteries, and it ends up being quite cost competitive. So I will say one of my colleagues from Maryland has spun up a startup company based on this technology that we've developed, and be continuing that process and that prototyping to bring this to manufacturing and to be able to actually realize these devices, these all ALD solid state batteries. Let's see. So the initial markets for these devices are the more cost insensitive markets where volumetric energy density is critical. Remember, these batteries are much smaller than conventional batteries because you optimize the performance by optimizing the materials, the connectivity, and the interfaces. So small sats, CubeSats, there's a big interest in some of these devices in CubeSats. And I will say the entire satellite and space-based market, there's an interest in not only CubeSats, but also rovers and deep space missions where auxiliary batteries on scientific payloads actually make a lot of sense, differentiating from a central lithium-ion battery, which has safety challenges during launch and during flight. And so small solid-state batteries integrated with devices and sensors on some of these satellites would really help optimization and help operation of these vehicles. Portable electronic devices, of course, is a huge market. And if you look at this picture up here, this is a smart dust image. This is a few years old, but here's your device up on top. This is your Photonics platform. This is the battery it's sitting on top of. And so the battery dominates that device. That's not a very useful piece of smart dust. It would be nice if you could integrate the battery into the device itself on the silicon and include that.